A grandfather clock keeps time using the steady swing of a pendulum. In physics, this kind of system is called a linear harmonic oscillator. But pendulums have a physical limitation. Their rhythm depends strictly on how they are pushed at the start, and they constantly lose energy to air resistance and friction. A tuning fork has the same problem. Strike it and it vibrates, but if you bump it, the rhythm changes or decays. Because it cannot generate its own energy, it requires external fine-tuning to stay on pitch. If biology relied on these linear mechanics, life would be precarious. A living body requires a rhythm that can take a physical hit and autonomously find its way back to baseline. Early radio engineers faced this exact problem. For a broadcast to work, the transmitter had to maintain a precise, unwavering frequency, something that early vacuum tube technology struggled to do. These vacuum tube oscillators were highly unstable. A slight voltage drop or physical vibration could knock the transmitter off its rhythm, effectively killing the broadcast. Balthasar van der Pol, a Dutch electrical engineer, began studying these circuits. He realized that the key to stability wasn't in making the hardware more precise, but in changing the underlying math to be nonlinear. Van der Pol found that by making friction a variable rather than a constant, he could create a system that corrected its own errors. This phase space graph plots position against velocity. A basic linear oscillator forms a perfectly circular, closed orbit. In linear systems, disruptions are permanent. If energy hits the oscillator, the orbit expands into a larger circle and stays there. The original rhythm is forever gone. Van der Pol's equation changes the damping, or friction, based on how far the oscillator has moved. When amplitude is null, damping is negative. It acts like anti-friction, pumping energy in, forcing weak rhythms to spiral outward. When amplitude gets too large, damping turns positive. It acts as heavy friction, bleeding energy away, forcing the orbit to tighten inward. This creates a self-regulating loop. The system balances energy creation and dissipation to maintain a steady pulse without any outside help. This self-balancing shape is known as a limit cycle. Because of this balance, the starting point doesn't matter. Whether the system begins from near stillness or extreme high-energy motion, the trajectories are all eventually pulled onto this single, stable loop. When nonlinear strength is increased to the extreme, the rhythm changes. It becomes a relaxation oscillation. Unlike a smooth sine wave, this rhythm is asymmetrical. It consists of a slow buildup of energy followed by a sudden, sharp release, creating a jagged sawtooth pattern. The math doesn't just suggest a rhythm, it enforces one. The result is a cycle that is remarkably difficult to break. Van der Pol noticed that this sawtooth rhythm appeared in more than just radio circuits. He observed this exact build and release cycle happening inside glowing neon lamps as they periodically flashed. By 1928, he had formalized how this math governed the storage and discharge of energy in resistors and capacitors. By solving a problem in electrical engineering, he had accidentally isolated a mathematical principle that applied to any system that stores and suddenly releases energy. Van der Pol realized his radio circuit's relaxation oscillation was a near-perfect match for the human heartbeat. To test the theory, he and his colleague J. van der Ark built an artificial heart using 3 linked Van der Pol oscillators. These represented the sinus node, the atrium, and the ventricle. The output of this artificial circuit was almost indistinguishable from a biological electrocardiogram. They were even able to simulate a skipped beat. They jolt the circuit, watch the rhythm stumble, and then watch the math force the system back to its steady baseline. This is why the heart can recover from a minor disruption. It is the physical manifestation of the limit cycle in action. Today, this equation is used to model everything from the firing of brain neurons to the way violin strings settle into a stable note. It is a mechanism that allows life and physics to remain consistent in an inconsistent world. True mathematical beauty is finding the same self-regulating formula inside a radio tube and the human chest.